Using risk-based inspection, RBI, for risk management and continuous improvement per API 580 recommended practice, enhancing safety through strategic inspection and risk assessment. Fundamentals of RBI and its role in engineering risk management. Risk-based inspection, RBI, is a structured and systematic methodology used to prioritize inspection activities based on the level of risk associated with equipment failure. As defined in API Recommended Practice 580 and 581, 2023, risk is the combination of the probability of failure, POF, and the consequence of failure, COF. RBI enables organizations to focus inspection and maintenance resources on equipment that poses the greatest risk to safety, environment, and business continuity, rather than applying uniform or time-based inspection intervals. This approach aligns with modern asset integrity management philosophies and supports informed, defensible engineering decisions. From an engineering perspective, RBI integrates knowledge of damage mechanisms, materials, operating conditions, inspection effectiveness, and historical performance. The probability of failure is influenced by factors such as corrosion rates, fatigue loading, creep exposure, and process variability, while consequences consider impacts including personnel safety, environmental release, production loss, and reputational damage. By quantifying or categorizing these elements, RBI provides a risk ranking that guides inspection planning. RBI does not eliminate risk, rather, it manages risk by reducing uncertainty through targeted inspection and data acquisition. Inspection activities improve confidence in the actual condition of equipment, allowing more accurate predictions of remaining life and safer operation. Importantly, RBI is applicable across the entire equipment lifecycle, from design and commissioning through operation, life extension, and decommissioning. In professional engineering practice, RBI supports compliance with regulatory expectations, demonstrates due diligence, and enhances communication between engineering, inspection, operations, and management. When implemented correctly, RBI contributes to improved safety performance, optimized inspection costs, reduced unplanned downtime, and better long-term asset reliability. As such, RBI is a cornerstone of risk-informed decision-making in industries such as oil and gas, petrochemical, power generation, and other process facilities. Identification of risk drivers and inspection optimization. A key strength of risk-based inspection is its ability to identify and evaluate the primary risk drivers that influence equipment integrity. According to API Recommended Practice, 2023, risk drivers are factors that significantly affect either the probability or the consequence of failure. On the probability side, these include operating temperature and pressure, process fluid composition, corrosion and erosion mechanisms, fatigue loading, material properties, fabrication quality, and historical inspection and failure data. Upset conditions, startup and shutdown cycles, and idle or standby periods are also important contributors to damage accumulation and uncertainty. On the consequence side, RBI evaluates the potential outcomes of failure, such as toxic or flammable releases, fire and explosion scenarios, environmental contamination, personnel exposure, and economic impacts including production loss and repair costs. Equipment located in high-occupancy areas or handling hazardous fluids will typically rank higher in consequence, even if the probability of failure is moderate. By systematically identifying these risk drivers, RBI enables inspection optimization. Inspection optimization involves selecting inspection methods that are effective for the anticipated damage mechanisms, determining appropriate inspection locations, and establishing inspection intervals that balance risk reduction with cost and practicality. Rather than increasing inspection frequency indiscriminately, RBI focuses on inspections that meaningfully reduce uncertainty and improve knowledge of equipment condition. For example, advanced non-destructive examination (NDE) techniques may be justified for high-risk components, while lower-risk equipment may require less frequent or simpler inspections. This targeted approach avoids overinspection, reduces unnecessary exposure of personnel, and ensures that inspection budgets are spent where they provide the greatest risk reduction. In this way, RBI serves as both a risk management and cost optimization tool, supporting sustainable and defensible inspection strategies in complex engineering environments. Using RBI to establish inspection plans, priorities, and residual risk awareness. Risk-based inspection plays a critical role in translating risk assessment results into practical inspection plans and priorities. Once equipment is ranked by risk, RBI outputs are used to define inspection scope, inspection methods, locations, and intervals. High-risk equipment is typically assigned more rigorous and frequent inspections, while lower-risk equipment may be inspected less often or with reduced scope. This prioritization ensures that limited inspection and engineering resources are aligned with actual risk exposure. Inspection planning through RBI also supports broader risk management by clarifying the limitations of inspection. Inspections reduce uncertainty by providing data on equipment condition. But they do not directly eliminate risk. Even after inspection, a level of residual risk remains due to factors such as human error, external events, design limitations, and unknown or poorly understood damage mechanisms. API guidance emphasizes the importance of recognizing and managing this residual risk rather than assuming inspection alone is sufficient. In situations where inspection cannot adequately control risk, such as equipment approaching end of life, susceptibility to brittle fracture, or very high consequence failure scenarios, RBI may indicate the need for additional risk mitigation measures. These may include changes in operating conditions, material upgrades, equipment replacement, protective systems, or procedural controls. RBI therefore supports informed decision-making by highlighting when inspection is appropriate and when alternative risk management actions are required. From an engineering management standpoint, RBI-based inspection planning improves transparency and traceability. Decisions regarding inspection intervals and methods can be justified based on documented risk assessments. Supporting regulatory compliance and internal governance. This structured approach enhances confidence in asset integrity decisions and promotes consistent application of risk management principles across the organization. Examples beyond inspection optimization. Beyond inspection planning, risk-based inspection provides valuable insights that support a wide range of risk management decisions. One important application is life extension assessment, where RBI is used to evaluate whether aging equipment can continue operating safely beyond its original design life. By understanding damage progression, remaining life, and consequence severity, engineers can determine whether continued operation is acceptable or if replacement is required. RBI is also useful in managing specific high-risk scenarios such as brittle fracture, where failure can occur without significant prior degradation. In such cases, RBI highlights the importance of operating temperature control, material toughness, and procedural safeguards, rather than relying solely on inspection. Similarly, RBI can inform decisions related to equipment with high economic or safety consequences, where even low probabilities of failure may be unacceptable. Another example is the evaluation of inspection deferrals or interval extensions. RBI provides a technical basis for assessing whether deferring an inspection will result in an acceptable level of risk, considering current condition knowledge and degradation rates. This capability is particularly valuable during turnaround planning or resource constraints. In all these examples, RBI serves as a decision support tool rather than a prescriptive checklist. It enables engineers and managers to compare risk levels, evaluate trade-offs, and select risk mitigation strategies that are proportionate and justified. This flexibility makes RBI a powerful component of integrated risk management systems in complex industrial operations. Continuous learning, reassessment, and improvement using RBI. API recommended practice emphasizes that risk-based inspection is not a one-time exercise, but a continuous improvement process. As new information becomes available, such as inspection findings, operational changes, process upsets, or failure incidents, the RBI assessment should be reviewed and updated. This iterative approach ensures that risk evaluations remain current and reflective of actual operating conditions. Continuous improvement through RBI involves learning from inspection results and failures to refine damage models, corrosion rates, and assumptions. For example, unexpected inspection findings may indicate that degradation is occurring faster or in different locations than previously assumed. Incorporating this information improves the accuracy of future risk assessments and inspection plans. RBI also supports adaptation to change. Modifications to process conditions, feedstock, operating limits, or equipment configuration can significantly alter risk profiles. RBI provides a structured framework for evaluating the impact of these changes and adjusting inspection and risk management strategies accordingly. From an organizational perspective, using RBI as a continuous improvement tool promotes a proactive risk culture. It encourages cross-functional collaboration between inspection, corrosion, operations, and engineering disciplines, and supports knowledge retention over the asset lifecycle. Over time, this approach leads to more reliable assets, fewer unplanned failures, and improved safety performance. In professional engineering practice, RBI-driven continuous improvement demonstrates commitment to excellence, responsible risk management, and long-term asset integrity.